trigonometric applications, so where we find different angles, etc., or work with equations or evaluate. Then we talked a little bit about the quotient identity. So quotient identity and square identity. We even did some proofs identity. And this is simply tan theta equals sine theta over cos theta, and the square identity is sine squared theta plus cos squared theta equals 1, which you can test using also a calculator, which was how we identified the pattern when we last did this on Monday. And then I think we did these examples. Okay, so we're going to use again trigonometric identities to solve, or rather to prove, right? Using identities to prove things. Right, to prove things. I'll just put that in comments. So we have to prove that 1 minus sine alpha divided by cos alpha equals cos alpha divided by 1 plus sine alpha. All right. So the first thing we need to set our boundaries, right? Where are our boundaries or limits? And these limits are limits for within which either right hand side or left hand side are valid mathematically. So why I say valid mathematically, or are valid, let's just say are valid. Valid so that if I have a fraction, this is a fraction, just as A over B is a fraction, I cannot have B equals 0. Why is that important? Why do you think this is important? Who wants to take a guess? Oh snap, Magdalene, I haven't shared with you. So yes, we revised Magdalene. It's trigonometry. We did identities, the quotient identity and square identity. Then we also did some examples, and then that last example we finished off led to this next one. The next one is this, So I'll just use a laser pointer. When we use identities, we can use them to prove things. And one of the examples we're given is to prove that 1 minus sine alpha over cos alpha equals cos alpha over 1 plus sine alpha. So we must prove that left hand side equals right hand side. But now we must start off first by identifying boundaries. What are these boundaries? One may ask. What are these limits? We know that when we're working with fractions, we should not have the denominator equal 0. Why? We shouldn't have denominator equal 0 Why is that? That is because so we must declare this because it's important. Because if this part of the equation equals 0, or this part of the fraction equals 0, ne? Then the fraction as a whole loses meaning, like it becomes undefined. What happens when you divide a number by 0? Eh? Hello? Magdalene's there.
It gives you error.
It gives you error, ne? Yes. So that error, ne? Musa, do you want to do a quick exercise? Let's do a quick exercise. I want to show you, and I like showing this one. It's not necessarily a proof, but it helps us think about, let's take the number 1, ne? And we divide it by 1. Ne? Let's start here. Let's start here. Ne? Let's take 1 and we divide it by 1. And then we're going to take 1 and divide it by 0.1. We're going to take 1 divided by 0.001. And then we're going to take 1 divided by 0.0001. Oh, let's start with 1 over 100. Then 1 over 10. So what's 1 divided by 100?
That's 1. Decimal.
Decimal, yeah.
0.01.
All right. And then what's 1 divided by 10? 1 divided by 10, sorry. What did I say? 0.1, okay. And then, oh snap, I should go back to here, because, okay, and then what's 1 divided by 1?
It's 1.
It's 1, okay. Then what's 1 divided by 0.1?
10.
Okay, and then what's 1 divided by, it's supposed to be 0.01, and then 1 divided by 0.001. Okay. Okay, so we're saying, so okay, let's start with 0.01.
100.
Okay, then 0.001 is 1,000, yes. Then 0.0001 is how much?
It's 10.
10,000, yes. 1, 2, 3, 4, 5. And then 1 divided by 0.00001.
100,000.
Eh?
It's 100,000.
100,000, okay. And 1 divided by 0.12345 What's this number? How big is, what's this number? What do we call this number?
Million.
It's what?
A million.
It's a million.
1 million.
Yes, it's 1 million. Okay, and what's 1 divided by 1, 2, 3, 4, 5, 6? Yeah.
Is it 10 million?
Yes, it's 10 million. Then what's 1 divided by 2, 4, 6. 1, 2, 3, 4, 5, 6, 7.
7. 7 is 100 million.
100 million. So how many zeros is that? 6, 7, 8. 10 to the power 8, yes? Then what's 1 divided by? So do you see? As this number gets closer, and you see we started when this number was very far from the number 0. The denominator started when we were very far from 0, ne?
Yes.
So on the other side of 0, where numbers are much larger than 0, when the denominator is much larger than the numerator, the answer that we gets smaller. Because 1 over 1,000, the number of zeros increases. 1 over 10,000, the number of zeros increases. Ne? Now we're getting closer and closer to 0. So at 1, then the number remains itself. But as we get closer to 0, between 1 and 0, it's here. From 1 to 0, it's here. As we get closer to 0, the answer increases for the fraction. As the denominator gets closer to 0, the answer increases. Closer to 0, it gets bigger and bigger and bigger and bigger and bigger. So if you have 1,000,000 zeros before the 1, then this number will be so large, so that if that number is 0 in and of itself, because you can't go anywhere close to 0, then that number becomes so large it's hard to quantify. At least that's what maths teaches us today. Maths as we know it today, or as it's taught today, tells us that. Yeah, one. So the reason we cannot have cos alpha or 1 plus sine alpha equals 0 is because if they are 0, then these fractions become so large we can't explain them, just as we did in this exercise here. That's the whole point of declaring these boundaries. So we must declare that to show that we are aware that our denominators must not equal 0. Every time you see these problems and you have a denominator and it's not a number that you know and it's an unknown, every problem in maths, when you see it, you must always, or maybe in algebra and trig and geometry maybe, etc., wherever you have a denominator, this must not equal 0, and you must always mention it. Always mention it, because when it does, then we get error, like you get on your calculator. Ne? So always put that. It'll get you that 1 extra mark that you might be needing, because it shows that you are aware that a denominator of a fraction must not equal 0. So you must start with declaring that. Then after, you can now get into proving your expression, right? You can get into proving your expression. And how do we do that? You can pick a side, really. You can pick a side. So we'll pick left-hand side, as in the textbook, just to illustrate, and say that our left-hand side equals 1 minus sine alpha over cos alpha. And we can multiply that by 1. And I'm going to show you how. So the same 1 minus 1 is 1 minus sine alpha over cos alpha, ne? We multiply it by the number 1. So any number divided by itself equals 1. That means x squared divided by x squared is 1. That also means x squared minus 1 over x squared minus 1 equals 1. Do you see that? Ne? So because in maths we have this, then we can multiply with 1 plus sine alpha over 1 plus sine alpha. And this way we manipulate this expression here by changing it without changing it. We transform it without changing it. We modify it rather without changing it. I don't know if that makes sense. And how we do that, obviously when you multiply this here with that, you get difference of two squares. And when you multiply this, you get something with cos and something with sine times cos. So we're going to do just that. And how we're going to get away with this, we can say at the top we have 1 minus sine alpha times 1 plus sine alpha. You remember when you have a minus b, extend call. Okay, our call is gonna end soon, so at some point I'm gonna ask us to start a new call, ne? So I just wanted to remind, to refresh this one. When we have this kind of multiplication, because that's what's going to happen here at the top here. That's what's going to happen here. Let me rather highlight it instead. So what's going to happen at the top here is this process here. Ne? So in that process, we have...
Another slide, please.
Oh, yes. Next slide. Yes. So at the top here, highlighted in blue, you're going to get this first, then outer, then inner, then last. I don't know if you know this. Did your educators ever teach you this? Eh? Aschual return to so.
No.
Distribution rule, multiplication of king, difference of two squares. Langbal return.
What, that one?
At least something yes so. Azanka like ruti, something yes so how to multiply these things.
Oh, you are brave. Yeah,
Lidiril. Oh, it's just not this way, ne? Okay, it's fine. I just wanted to know if you are familiar with it. So what happens is we're gonna get 1 minus sine squared alpha. At least in grade 11, grade 10, grade 12, sorry, in grade 11 and 12, we should be able to do difference of two squares. So I'll just go from that. So at the top, we have 1 minus sine squared alpha over cos alpha times 1 plus sine alpha, right? And if you recall correctly, when we have sine squared theta plus cos squared theta, that is the square identity and it equals 1. And also we can manipulate this expression and have cos squared theta equals 1 minus sine squared theta. And this is what we can transfer there, such that the left hand side equals cos squared alpha over cos alpha into 1 plus sine alpha, and these divide each other out like that, so that we are only left with cos alpha over 1 plus sine alpha, and that equals the right hand side. Therefore, we've proven that the left hand side equals that 1 minus sine alpha over cos alpha equals cos alpha over 1 plus sine alpha, which is this expression here. Do you think we can do it in the opposite direction, starting with the right hand side? Let's try it. So we can try it with the right hand side, right? We can say cos alpha over 1, sorry about that. Oof, tired. So then it can be cos alpha over 1 minus, or 1 plus rather, sine alpha. Can we multiply it with over 1 minus sine alpha? That equals 1, by the way. So that we have 1 minus sine squared alpha over cos alpha into 1 minus sine alpha, and this is cos alpha over 1 minus sine alpha over cos squared alpha, and that becomes 1 minus sine alpha over cos alpha, and that equals left hand side. So yes, it does work in the other direction. Can you see that? All right, so I'm gonna start a new meeting now. Then we'll join in just now, né? Until like 8ish. All right, so you can leave this one, and then I'll set up a new quick meeting quick. Okay. Turn the home screen. Alright, welcome Musa. Alright, so I wanna like the same example we did, ne? I'm gonna need you to have your mics on so that re kgone ho bolela, ne, as if you're here with me. And what we're gonna do problems that are showing now on our screen, like reduce and prove, ne? The reason for that is so that we get familiar with these types of questions, because Musa, I believe what you wanna rank trigonometry, these types of things, they always go for like 8 marks. Yeah. Let me just show Olaning. What's her name? Magdalene. For an example, keep mind the gap in, eh? All right, yeah. Again, this is reduction. Pa 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 pa. You see, so these skills that we're learning, okay, maybe not there. Oh yeah, you see, 4 marks, 7 marks, 6 marks, 5 marks, so what? And these are all the same types of problems that you find first and foremost in grade 11, you see? So that's nice, because at least we're expected to know how to maneuver these types of problems, where you just have to prove by choosing either left-hand side or right-hand side and simplify it so it looks on the one side. If both sides look difficult, try simplify on both sides until you get to a same point. And it's easy. You just use your square and quotient identities, and yeah. And you can factorize as well. FOIL, like difference of two squares, etc. All of those tricks that you learned in algebra, you can use them to manipulate these trig identity things. So I want us to do a few of these exercises until refelele jaga 80. So we'll start here, right? Trig problems. We'll use trig identities, or rather, yes, to reduce. Ladies, you girls, do you know what the meaning of reduce is? Go focus again. Why were we really focus? Why were we really focus? Because A to 1 trigonometric ratio, ne? Reduce to 1 trig ratio. Remember, trig ratio, there is only sine, or rather, let me not say only, there's sine, cos, tan. There is also cosec, sec, and cotan. Remember these. So we must reduce the following to 1 trig ratio. Yamatomo ki sine alpha over tan alpha. Remember in so Musa, I'm gonna point you to mind the gap, ne? Because on page 207, ne, that's your grade 12 work. So I just wanna share that in grade 11 you already do these things, so you do get examined in them in matric and your final exam. So Magdalene, just be ready for them. So if you master them now, you'll cruise through them in matric. And if you can, share with your friends whom you're in class with, whom you do these kinds of problems with from time to time. But anyway, this one you can solve by saying sine alpha. But then tan alpha can also be written as sine alpha over cos alpha. So this part here is still tan because tan is a quotient identity. Né? So we can simply say because tan theta equals sine theta over cos theta, then I can substitute where I see tan, I can substitute sine over cos. Then this becomes sine alpha over 1 multiplied by cos alpha over sine alpha. Why? Because when we have A over B divide by C over D, this equals A over B multiplied by the inverse of the denominator. And these divide to give 1, and we're only left with cos alpha. So at this point, we ask ourselves, did we meet the goal of reducing this expression to one trigonometric ratio? Yes, we did. And we'll get full marks. Full marks. Alright? So do you see how we can do these problems? The second one is we can do this one. D, which is 1 over cos squared beta over cos squared beta minus tan squared beta. Remember, we've got square identity and trig identity. Square identity is sine squared theta plus cos squared theta equals 1. And also quotient identity is sine theta over cos theta. So here, if we make sine the subject of the formula, then we have sine squared theta equals 1 minus cos squared theta. And that closely resembles something like that. So we'll have sine squared beta over cos squared beta minus tan squared beta. And this tells us that this is tan squared beta minus tan squared beta, and that gives us 0. Interestingly enough. So we get 0 here. Note that this doesn't say that cos squared beta is 0. It just tells us that the result of reducing this to one trigonometric ratio gives us 0. Doesn't say that this denominator is 0. Ne? Just be careful of that. We can do the ones that require us to prove. Those are usually longer. So the first one is the same as the example we did, so we will not do that. But we must prove that, I guess, left-hand side equals right-hand side. We must prove that. And let's say we've got B. Let's do B. So it's sine squared alpha plus cos alpha minus tan alpha into cos alpha plus tan alpha equals 1 minus tan squared alpha. Which side do you want us to choose? Anyone? Left-hand side or right-hand side?
How about the next slide?
Oh, next slide.
Right-hand side.
Yes, so we're doing this one here. Should we choose left-hand side or right-hand side? Which one should we choose? Left or right? Which one?
Right.
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 Okay, so we'll do right-hand side. Okay. Remember, it's not always that we will, and I'll share why, ne? Because sometimes you will have two, and I'll just pull this up here. If both sides look difficult, you can try simplify on both sides until you reach a point where both sides are the same. So I'm gonna go with that strategy. Such that this here gives us cos squared alpha minus tan squared alpha. And this is tan squared alpha. And this here gives us 1, which equals right-hand side. So if we do right-hand side, we can go 1 equals and between these two, we can take difference of 2 squares, and it's cos alpha minus plus tan alpha So it's just being creative enough to identify that that is a square identity still, and this equals left-hand side. And once we do that, then we give room to have a cos squared and a tan squared, which we can factorize, and it gives us those factors there. So that's how one could think about it if we prove right-hand side or left-hand side. We'll do C. I'll challenge myself this time around. So 1 over cos theta minus cos theta tan squared theta over 1 equals cos theta. So if we start with right-hand side, I want to get to a point where I have, so 1 over cos is sec, but I don't want to go there. If I multiply this by tan squared over tan squared, okay, maybe not. On the other side, we've got a denominator of cos. So maybe let me multiply with something that has cos. So let me multiply with cos squared theta over cos squared theta. I'll just do the obvious. And this gives me 1 minus sine squared theta over cos squared theta times cos theta. This will divide that, and I still have a cos squared theta there. And then I'm left with cos squared theta into 1 minus sine squared theta over cos of theta. Then I can separate I can say cos squared theta minus cos squared theta times sine squared theta over cos theta. I can have cos squared theta over cos theta minus cos squared theta times sine squared theta over cos of theta, ne? And this equals, what did I do? Obviously those are gonna cancel, and then I have cos theta times sine squared. There's something I shouldn't have done right here. When I erase this, and start, and I'll say this is cos theta over 1 multiplied by 1 minus sine squared theta over cos squared theta. Ne? Then I'll have cos theta minus cos theta times sine squared theta. All of this is over cos squared theta. And then I have cos theta over cos squared theta minus cos theta times sine squared theta over cos squared theta. That's what we get. Then these divide like that, and this is tan. So this then becomes 1 over cos theta minus cos theta tan squared theta over 1, which equals left hand side. Do you see that?
Now I'm confused actually.
Are you seeing Jamboard? Let's start there.
Yeah.
Oh, okay, cool. You want me to run through the problem again?
Yeah, area number C, please.
Number C. Okay, where did I confuse you? Point to me where I confused you. Which step? There's 1, 2. Otomamu. Remember our goal?
Yeah, because
our goal is to prove that left-hand side equals... Remember our goal is to prove that left-hand side equals right-hand side, again? Prove the following identities and state restrictions where appropriate. Ne? Alright, so that's our goal. So firstly, cos theta must not equal 0. That's our restriction. And I think here our restriction was... we didn't have a restriction here. It wasn't necessary. But here it's necessary because we have a fraction. So when we have a fraction, we look at the denominator, and that denominator, because we don't know the angle, must not give us 0. Alright, so we start. 1 over cos theta minus the cos theta times tan squared theta over 1 must equal cos theta. That's what we must prove again. So the last example, I said we'll start with the right hand side, but then I dodged Kaloropa and I did left hand side instead. So I said this time around we'll challenge ourselves and start with the right hand side, which equals cos theta. And we must prove that this cos theta is the same as this on the left hand side. Can you see that? Can you see what we have to do?
Yeah, boss.
Alright. So then we say cos theta is the same as cos theta multiplied by cos squared theta over cos squared theta. Remember that step. It's this one here on slide 7. Sorry.
Okay.
Sorry. I said cos theta is the same as cos theta times cos squared theta over cos squared theta because this equals 1. Ne? So I'll just say in brackets cos squared theta over cos squared theta equals 1. So it doesn't really change the original expression. The original expression still remains the same. It's just multiplied with this. But we're multiplying with this so that we can get to our goal. So we're testing out if this works. Then that is the same as in this slide here, slide 7, sorry. That's this step here. This step here. Can you see it?
Yeah, I can see it.
Right. So far we are following, ne? Right. Then the next step is to expand using a square identity, that one right there. So cos squared theta equals 1 minus sine squared theta, because the square identity is sine squared theta plus cos squared theta equals 1. So if we apply additive inverses on the square identity, we can have then on our right hand side cos theta times 1 minus sine squared theta. And then we're going to have a situation at distributive rule. We still keep the denominator. You see that step, Magdalena?
Yeah, but I see it now.
Right. It's this step here. Musalwana wa bona ke. Musa, don't be quiet. We are talking with you in the same class.
Yeah.
Arba banchi, so don't be shy. Alright, so you see that third step, I guess. Then the fourth step, we are going to multiply cos by 1 and cos by negative sine squared. So we're going to have cos theta minus cos theta times sine squared theta, and all of this is divided by cos squared theta. Is that the part that was confusing? Eh? Do you see how that is possible? I just multiplied cos with 1 and I multiplied cos with negative sine squared.
Oh, okay. What I know so.
Is that what the confusion was in this step?
Yeah, I think really namanoso kay
And that move right there is grade 7, grade 8, king grade 8, 9, grade 8, 9, 10. That simple step, this one, is grade 7, king 8, 9, 10. This step. It's grade 8, 9, 10 maths, né? Then what we can do is separate the fraction. So how we do it, a plus b over c is the same as a over c plus b over c. And what we do is cos theta over cos squared theta minus cos theta times sine squared theta over cos squared theta. This, can you see that? This is one fraction and this is another fraction. So this fraction is this one. So let me use blue pens instead. So this is this. And I'll use a green pen for this other one. So this one is this one. So we just separated the two fractions. There's two fractions in one, and we just separate it into two fractions that are two fractions. Can you see that?
Yep.
Yes, this is fractions as we learned them from grade 8, 9, and maybe 10. We're just using that same method of computing in trigonometry. Then what happens is Jeki ovally division, and what we end, or rather ovally division moki, and then here we can use quotient identity here. We're getting closer to that we're seeing there. So we want to say cos divided by cos squared gives us 1 over cos theta minus cos theta times tan squared theta over 1. And that tan squared, Shion. You see it? So that's that step here. You see, that's that step here. Do you see it? Do you follow? And at this point, we can conclude that we've proven that our left-hand side equals right-hand side. So, kgopola re mishe mo bana ba gesho, bana ba ntate.